Welcome to solverfy.
So we have a graph here that represents two different things. We've got the molecular speed of a gas on the x-axis, and we've got the relative number of molecules going at that speed on the y-axis. Now we want to know which curve fits a gas at a lower temperature. So we need to make a couple connections. We need to first know that a gas's kinetic energy is directly proportionate to its temperature in Kelvin. And we also need to know that as kinetic energy goes up, so does the speed. So as kinetic energy goes up, so does the speed. So that also means that as temperature increases, so does speed. As temperature increases, kinetic energy increases, and so does speed. As temperature decreases, gets colder, so does its kinetic energy, goes slower, speed is slower. So if we want to know which curve fits a gas at a lower temperature, we have to look and see which one has a lower speed. And we would say that our red curve does. Our red curve is representative of a lower speed. And in our second question, we want to know which curve depicts a gas of a higher kinetic energy. So we've essentially just answered this question. We know that a higher kinetic energy is going to be related to a higher temperature and a higher speed. But we can explain this with a little bit of math, just a little bit. So we've got kinetic energy, average kinetic energy, oops, wrong symbol, equals, okay, so an average kinetic energy equals two-thirds R over Na times T. Now, if we break this down, we've got essentially three constants and our temperature. We've got two-thirds, which is a constant. We've got R, which is 8.314 joules per mole times K. And then we've got Na, which is Avogadro's number, and that is 6.022 times 10 to the 23rd. So looking at this, we've got essentially one big constant right here. We've got two-thirds a constant multiplied by R constant divided by Na a constant, all a constant. So we know that Ek is really only influenced by our temperature. Ek and temperature are directly related by this logic. Constant times a high temperature gives us a higher kinetic energy. So our question, going back to that, which curve depicts a higher kinetic energy? Well, we would say that the curve with the higher temperature and higher speed. Because remember, we know that higher temperature and higher speed, higher kinetic energy, all the same thing. So increasing temperature, increasing kinetic energy, increase in speed. The answer to which curve depicts a higher kinetic energy is going to be the one with the higher temperature and higher speed. We've also got the third question. Our third question asks us which of these gases is going to have a higher diffusion rate. We're going to follow a similar kind of logic. We know that a diffusion rate is essentially dependent on the amount of collisions we have. So a higher diffusion rate, so higher diffusion rate is going to be equal to a higher collision frequency. And we have an equation to find our collision frequency. So down here we've got our collision frequency equals our most probable speed and I'll stop for a second and explain. Our most probable speed is going to be our highest relative number of molecules. So wherever the peak of these curves is going to be our most probable speed. And of course, we'll get our speed from our x-axis. Most probable from the y, and that speed from the x-axis. And now going back down here, collision frequency equals most probable speed divided by mean free path. And our mean free path is a little bit complicated to figure out. So, and for all intents and purposes, we don't need to know it to figure out our collision frequency. We do, however, need to know that mean free path won't change based on our temperature change. So nothing that we change in this problem will influence our mean free path. So for all intents and purposes, that number will remain the same. The only thing that we will change will be this top number here, our most probable speed. So if we look back at our graphs, I'll use red for our red graph or curve. We will have a probable speed of, let's just say this is some lower number. We'll use a number like 5. So our most probable speed, 5 meters per second. Now this is not accurate. These molecules or any particles will be going a lot faster than this. We're just going to use this as a simple explanation. So 5 is our most probable speed divided by, since mean free path is usually a small number less than 1, we'll use something simple like 0.5. So if we divide 5 by 0.5, we'll end up with 10. So a simple arbitrary number like 10 for our collision frequency. In reality, this number will be a lot higher. But for this, we will just explain it using simple numbers to give us a simple look at what we're trying to figure out. Now for our blue curve, we see that we've got relative number of molecules is a little bit lower, but the peak of our graph lies at a higher speed. So for our higher speed, most probable speed, we'll use, say, 10 meters per second, and we'll divide that by the same number because remember, mean free path won't change based on what we're given. So 10 divided by 0.5 equals 20. So if we take those back over to this original equation, most probable speed divided by mean free path gives us collision frequency, and we know a higher collision frequency gives us a higher diffusion rate. We know that a higher most probable speed will give us a higher collision frequency and a higher diffusion rate. So the answer to this problem is we would expect our blue curve to give us a higher diffusion rate. Higher diffusion rate, higher collision frequency, higher temperature, higher kinetic energy, higher speed. These things will all be related. Lower kinetic energy, lower temperature, lower speed, lower collision frequency, and lower diffusion rate.